All right, chapter 14, our last chapter of the semester. And we're going to be talking about ideals and factor rings. We've heard the word factor before, back when we were talking about factor groups. And in order to get a factor group, we needed to have a normal subgroup. So ideals are going to kind of be similar to this idea of normal subgroups, and ideals will be needed for our factor rings. So let's get started with chapter 14 with some definitions. So a subring A of a ring R is called a two-sided ideal of R if for every R in R and every A in A, both RA and AR are in A. Basically, a subring A of a ring R is an ideal of R if A basically absorbs elements from R. So RA is equal to elements RA such that A is an A. And that is a subgroup of A, subset of A. And AR is equal to the set AR such that A is an element of A, and that is a subset of A, and that is for all elements R of R. Now, an ideal is a proper ideal if RA is a proper subset of A and AR is a proper subset of A. So we have subrings going on here, and we're saying that they are ideals if RA and AR are both in A. Now we have a test to see if something is an ideal. So theorem 14.1, the ideal test. A non-empty subset A of a ring R is an ideal of R if A minus B is an element of A whenever A and B are elements of A, and RA and AR are an A whenever A is an A and R is an R. So this is our ideal test. So some examples of ideals. Example 1, for any ring R, our trivial subring and the whole ring itself is an ideal of R. The ideal, which is the trivial subring, is called the trivial ideal. For any positive integer n, the set nz is an ideal of Z. Now, if we let Rx denote the set of all polynomials with real coefficients, doesn't have to be integer coefficients this time. We've dealt with Zx before, but here we just have to have real coefficients, and we are dealing with polynomials. And we let A denote the subset of polynomials with constant term of 0. Then A is an ideal of Rx, and A is equal to the cyclic subgroup generated by X. Now this brings us into factorings. So theorem 14.2, the existence of factorings. So let R be a ring and let A be a subring of R. The set of cosets, R plus A such that R is in R, is a ring under the operations, and it gives us additive operations and multiplicative operations. And then it says if and only if A is an ideal of R. So it shows us both our additive and multiplicative operations, which I'm guessing are exactly what you figured they would be based on our idea of what a factor group was previously. So to kind of get our hands dirty a little bit here, we're going to look at example 4, and we are going to look at the factoring listed here. And we have 0 plus 4z, 1 plus 4z, 2 plus 4z, and 3 plus 4z. And let's practice performing operations within this factoring. We're going to do one that's under addition and one that's under multiplication. So for addition, we'd be saying add 2 and 3 together, and we'd have 5 plus 4z. But what is that really equal to? That's really equal to 1 plus 4z. And with our multiplication, we'd be doing 2 times 3, and we'd have 6 plus 4z, which is really just 2 plus 4z. And we're able to simplify these because we know that we're absorbing things of multiples of 4. And we actually just noticed that, hey, we're doing operations mod 4, right? All of our operations here, and I broke it down here for you, nicely typed out. All of our operations that we're doing are going to be mod 4. We took 2 plus 3, we got 5, and we simplified that to 1. We took 2 times 3, we got 6. That was really just 2. Let's keep this idea that this looks like we're doing mod 4 in our head for later on. We're going to come back and reference this. So, a prime ideal A of a commutative ring R is a proper ideal of R such that AB is an element of R and AB is an element of A. It implies that A is an element of A or B is an element of A. And a maximal ideal of a commutative ring R is a proper ideal of R such that whenever B is an ideal of R and A is a subset of B is a subset of R, then B either equals A or B equals R. So, example time again. Let n be an integer greater than 1. Then in the ring of integers, the ideal nz is prime if and only if n is prime. Note here that the trivial ideal is also a prime ideal of the integers. So let's look at the lattice of ideals for Z36. What are the maximal ideals? Well, when we're looking at our lattices, we're really saying which ones are there at the top. Which ideals do we have where there's no ideal that contains it except for the whole ring itself? So by looking at this, we see that it's just 2 and 3. So only the cyclic ring generated by 2 and the cyclic ring generated by 3 are maximal. And then we have a couple interesting theorems here at the end Theorem 14.3, it talks about integral domains, if and only if A is prime, and then fields if and only if A is maximal. And comparing these two is going to be helpful to us in one of our examples when we're trying to show that something is either an integral domain and is an integral domain but not a field. This is chapter 14, and we're going to do some examples for chapter 14 in our next video. If you have questions, make sure that you let me know.